In our discussion so far, as far as sequential circuits are concerned, we have come across a number of flip-flops: the SR flip-flop, the D flip-flop, the JK flip-flop, and the T flip-flop. Of course, we have used some flip-flops a little more than the others, but that does not mean that what we have used less is not important. So therefore, the question is that, is there any kind of relationship between these flip-flops? Is there any kind of relationship between these flip-flops? So suppose I ask a question: can we make a D flip-flop using a JK flip-flop? So let's first write the characteristic table or the state table of each of these flip-flops. So for a D flip-flop, the characteristic table looks like this. And for a JK, the state table looks like this. So what we notice is, for the D flip-flop, the next state is equal to the D, that is 0 and 1. When we look at the state table of the JK flip-flop, we see that Q is having the values 0 and 1 over here. That is, these two rows are corresponding to the outputs or the next state of the D flip-flop. So therefore, it's like saying these two rows can be correlated with the D. However, the biggest difference between these two flip-flops is that the D flip-flop has one input, D, and the JK flip-flop has two inputs, J and K. Now we have to use the JK flip-flop to make a D flip-flop. So therefore, it's like saying we are given a JK flip-flop already. We are given a JK flip-flop, and we have to use this to make a black box where the input will be D. So it's like saying the input D over here has to be kind of translated into J and K. So corresponding to 0 and 1, the values of D would also be 0 and 1. So it's like saying, if I now correlate D with J and K, whatever is D, the same as J. Here D is 0 and 1, here J is 0 and 1. So therefore, I will say whatever is D, the same as J. And K is now 1 and 0. So whatever is D, K is just the complement. So K will be equal to D bar. So I will just pass D through a NOT gate and give it to K. Of course, there will be some clock, either positive or negative is triggered. In this particular case, it does not really matter. So this was fairly simple. Now suppose I ask, design a JK flip-flop using a D flip-flop. That is the converse of the question. JK flip-flop using a D flip-flop? Can we do this? So it's like saying here we will now have a D flip-flop and we have to somehow correlate J and K together to D. Now that seems a little bit more difficult because in some combination J and K have to be used to realize D, which is a little more difficult than what we did over here. So therefore, this is not so easy. And in general, when you're converting, let us say, when you're realizing one flip-flop using another flip-flop, we may not be fortunate enough to see this kind of a correlation. We may not be always fortunate enough to see this kind of a correlation. So therefore, we need to develop a generalized methodology to design one kind of flip-flop using another kind. Generalized method is needed. So let's say to realize a type X flip-flop using type Y flip-flop. So the flip-flop that you want to realize and the flip-flop that you will use to realize, the two are different. So whenever you have this kind of a problem, this is a very simple method. You need to have the state table of the flip-flop that you want to realize. And the flip-flop that you want to use to realize the type X flip-flop, for that you need to have its excitation table. So therefore, let us say we will do this problem. We want to realize a JK flip-flop using a D flip-flop. So therefore, we will need the state table of the JK flip-flop and the excitation table of the D flip-flop. So for the JK flip-flop, the state table is this. Now the excitation table for the D flip-flop means, given the present and the desired next state, what will be the required values of D? It will be the same as Q plus. So now we will proceed in a way that is very similar to the design of a synchronous sequential circuit. So therefore what we will do is we need to expand this. So JK, let me also use the present state as a variable and the next state. Zero, zero, zero. These are the inputs. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So when J and K are 0, Q plus will be whatever is Q. This is 0 and 1. When J and K are 0 and 1, Q plus will be always 0 irrespective of Q. Here for 1 and 0, it will be both 1 irrespective of q. And here it will be q bar, that is 1 and 0 when j and k are both 1. Now looking at this q and q plus, we need to write the value of d using the excitation table. But there is nothing much to do. D is same as q plus. So 0, 1, 0, 0, 1, 1, 1, 0. So therefore what have we seen? We have now been able to express D as a function of j, k and q. So I can say D is a function of j, k and q, where the midterms are 1, 4, 5 and 6. So if we just construct a K-map, this is what it is. So we can make one group over here, the other group over here. So we'll get D equals j q bar plus k bar q. So therefore, we have a D flip-flop which you're going to be using to realize this GK flip-flop, Q1 Q bar. So we will need, first of all, an OR gate and two AND gates. So the first input will be J and Q bar. So Q bar we can bring from here. And K input can be passed through a NOT gate, and Q we need, which we can bring from here. So this Q input will come from here like this, and of course we always have the clock. So the user from the outside view sees that the inputs are J and K and the outputs are Q and Q bar. This is finally Q and Q bar. So using a D flip-flop, you can realize a JK flip-flop. So like this, you can use this technique and extend it to realize any kind of flip-flop with any other kind of flip-flop. So I encourage you to try realizing a T flip-flop using a JK flip-flop, or a JK using a T, or a D using an SR, and so on. You will definitely come across some very, very interesting results. So now, let us now see how flip-flops can be used as memory elements. flip-flops as memory elements to store data. Suppose I have a simple flip-flop like a D flip-flop. So for this D flip-flop, the state table is this. Now what does this mean? What this means is, suppose I have a D flip-flop Now, whatever is the value of D, that will be considered when the clock edge comes. In this case, the positive clock edge. And that value of D, which is there during the positive clock edge, will be given to Q. And this value of Q will continue to stay at that old value, irrespective of whether D changes or not. But it will continue to stay the same until the next positive clock edge comes. So this is the way in which this flip-flop can be used as a memory element. So this is the way. This is the way where we can use the clock as a synchronizing signal to tell this element that, okay, now the new memory value, the new value that has to be stored is now given on D. Now I am giving the clock edge, whatever is the value at D, you will put it to Q and Q bar. Of course, with complementing values. So therefore, this entire thing can be used to store one bit of data. Why one bit? Because the value that we are giving to D is a 1-bit value, and the values that is taken by Q is also a 1-bit value, and that is what is being stored. And that storage will happen between two successive clocks. Now suppose the clock is totally in our control. We will decide when we will give the clock for this to take a new value. And at all other times, the value will be stored to the last updated value irrespective of D. Now, we have already seen a glimpse of how this works with waveforms a few lectures ago. When there is no clock edge, no matter how much D changes, Q will never ever change. This change will only happen at clock edges. Alright? So using this, let us see how we can design a circuit to store more number of bits. Let us see a circuit, or rather, let's before going over there, let us try to understand what essentially happens. So if my clock is like this, I give a clock edge and then I fall silent for some time, and again I give a clock edge. Positive edge triggered flip-flop. Now whatever is the D value, the D value has to be stabilized before the clock edge comes. If it is not stabilized and both clock and D are changing at the same time, then we don't really know what will happen. So therefore, let us say the value of D will be settled at 1 beforehand, and then it comes to 0. So the Q value, let us say, which is 0, will continue to be 0 until the clock edge. Now at the clock edge, it will sample the value of D. It will see it is 1. So therefore, Q will become 1. And this one will continue to stay until the next positive edge. Now during this time, whether D changes or does not change, it does not matter. The value of Q will not change. So these changes are ignored. Then whatever is the value of D over here, let us say it is 0. It is changing later. The value of D at this clock edge will be considered, which is 0, and therefore Q would become 0 and will continue to stay 0 until the next clock edge, the next positive clock edge comes. So now let us continue the question which we had raised, that is how we can use this concept to essentially store more number of bits. How we can use this concept to essentially store more number of bits. So as you know, these days 1 bit of data is nothing. 1 bit of data is nothing. So when we say 1 bit, it is like it's a single binary digit. When you have 4 bits of data, that is called as a nibble or 1 nibble. 8 bits is called 1 byte. 8 bits is called a byte. So likewise, you can have even bigger sizes, that is 1 kilobyte or KB is 1024 bytes. Remember, it is not 1000, it is assigned as a power of 2. So 1024 is 2 raised to 10. So therefore 1024 bytes is 1 kilobyte. Like this 1 megabyte or 1 MB, that is 1024 kilobytes. So that is in terms of bytes, that is 1048576 bytes. So little over a million. That's how it's supposed to be. Like this 1 gigabyte or 1 GB is 1024 megabytes. So I leave it to you as an exercise to convert this into bytes and check how many bytes it will be. So now let us see a simple circuit through which we can extend that 1 bit storage capability of the D flip-flop into storing more than 1 bits. Into storing more than 1 bits. So let us have a synchronous circuit which looks like this. I have, let us say, 4 D flip-flops. I want to store 4 bits of data. So let's call this as D0, Q0 and Q0 bar, D1, Q1 and Q1 bar, D2, Q2 and Q2 bar, D3, Q3 and Q3 bar. Let us say all of these have a positive edge triggered clock. And all of them are getting the same clock, which makes it a synchronous sequential circuit. And I give some value to D, that is called X. X can change. But whatever is Q0, the same goes to D1. Whatever is Q1, that goes to D2. Whatever is Q2, that goes to D3. And Q3 is left unconnected to anything. So now let us try to see how this circuit would behave. Now suppose I have clock which looks like this. Let us say I have 4 clock edges, all of which are, and out of this I have marked only the positive edges. And let's suppose X, the data line X, changes in a certain way. Let us say at every positive clock edge, the value of X is stabilized. So let us say initially it becomes 1, then 0, then again it goes to 1, like this. So now let us try to see what will be each of the Q values. Now whatever is X, that is D0. So we should write D0 in bracket. Now at this time in the first clock edge, we will see whatever is the value of D0, and that will be Q0. So initially if it is 0, this will stay as Q0 until this point and then become 1. And this will persist until the next clock edge. Over here, the value of D0 is 0. So therefore Q0 would also become 0. Then in the third clock edge, we see D0 is 1. Then it will become 1. Fourth clock edge also, it will continue to be 1. Now what you see, whatever is X or whatever is D0, the same is Q0 except that there is a time delay. Which is why again D is called as the delay flip-flop. Now what about Q1? There are 4 flip-flops. We have to see what happens for each of those state values. We have to see what happens for each of those state values. So what we see is for Q1, whatever is D0, whatever is D0, whatever is Q0, that will be D1. Now what are we saying? Let us say initially Q1 is 0. Here clock edge is changing and at the same time Q0 is changing. So now we are in a bit of a fix. What should we do? Well, the answer is very, very simple. For the first flip-flop, for D0, this Q0 was responding to this clock edge. So therefore, when we are considering for Q1 at the same clock edge, it will be the old value of Q0 which will be considered. So the old value of Q0 was the value which was there before the clock edge. So therefore, what will happen is this old value which is 0 before the clock edge, that will be considered and that will be D1. So therefore for this clock edge, Q1 will be 0. Now at this clock edge, again what we see, at this edge there is a transition. So which value should we choose? We should choose the previous value. Please note, this need not always happen. Here we are choosing the previous value because each stage is interdependent on the output of the previous stage. So therefore we will choose the value of Q0, that is D1, before this clock edge, that was 1. So therefore this one will now come here. And then here again we will choose the old value which is 0. And then this one. Next we will look at Q2. Q2, depends on D2, which is nothing but Q1. This is D2. So therefore, here it's very, very simple. It will continue to be 0. Again, here we have two transitions. So we'll consider the old value, which is 0, and then it will come here. Here again, at the transition, we'll consider the old value of 1. So this will become 1. And then here the old value is 0. So this will become 0. Finally, Q3. This is what it will look like. So finally, after 4 clocks have come, what are we seeing? We are seeing initially between 2 clock edges the value of x is 1, then it becomes 0. Again over here it becomes 1, again here it becomes 1. Now when we look at the value of Q3, Q2, Q1, Q0, after these 4 clocks have come, the value is 1, 0, 1, 1, which is the same as the way x has been changing. So whatever is the value of x, we see that after that many clocks, this is being stored in each of these flip-flops in this order. So what we have done, we are able to store 4 bits of data into this circuit by giving 4 clocks. So this is called as a shift register. Why? Because the data is essentially shifting from one point to another point. And after n number of clocks, all the flip-flops have the required data that is being stored. So therefore, you can use this shift register to store n bits of data. The only drawback is you will need n bits or n clock edges to do so. So therefore, it is slower. So when you look at this, you can see that essentially this shift register can be used to store data, but there is one more advantage it gives. Let us see what happens when we have more number of clocks. So again, we will mark only the positive edges. We will have the same x as before. So whatever it is, after this we are not really considered. So Q0, as we saw, will be something of this kind. Then Q1 we saw would be something like this. Now what will happen after this? After this edge, it will become 1 and will continue to be so for the next 2 clocks. Here also we will get. Because this will be easily 1 until this point, irrespective of what the value of x is. So therefore, this will continue to be 1, Q1 until this point. What about Q2? Q2 will be initially 0. Over here, we will have this, and then the 0, and then the 1 for the next 2 clocks at least, until this point. Finally, Q3 will be 0 initially. Then over here it will become 1, as we had seen the last time. Then this will become 0. Then at this point it will become 1. And then it will stay like this for at least 2 clocks till this point. If you look at Q3, the data is again 1, 0, 1, 1 at these different clocks, which is the same as X. So what we are saying essentially is that Q3 is nothing but just a delayed version of X. So therefore, you can actually use this circuit. You can actually use this circuit to sort of use it as a delay line, or as a, if you have a stream of bits which you want to send but with some delay, then this is the circuit you use. So if you want delay by n number of clocks, you have to use n number of flip-flops. So this is called as a delay line. Okay. Now, having established this, let us try to learn a little bit about memory. Let us try to learn a little bit about memory. What we saw as a shift register, it is also memory, yes. But if we need to store large number of bits, then we will need large number of clocks also. So therefore, most memory systems where large amount of data is stored in these days, they are usually not clock driven. They make use of storage but without clock. So we already know the basic idea of how to store something without clock, that is using the basic butterfly structure, that is that for a latch. Okay, so but before we discuss that, let's suppose I want to store some data in the memory. So in that case, let us say I have some numbers which I would like to store. I have some numbers which I would like to store. They can be any numbers. Let us say I need to store some 8-bit numbers. Now I need to store some 8-bit numbers. Okay. Let us say I have a class of students essentially, and let us say the 8-bit number is a unique identifier of the students. Okay, so it can be any number. It need not be an ordered number sequence as such. Now let us say there are a total of 128 students. Or let us say it need not be even a unique identifier. Let us say I am denoting the marks the students have obtained in their exam as an 8-bit binary number. Okay. So there are 128 students. So let us say I want to store it like how I store it in a notebook. So this is the first location. Then this is the second location. This is the third location, and so on. So therefore, if I have to store for 128 students, I will have 128 such locations. Okay, so let us say if I have to store some 8-bit numbers, then the maximum number that can be stored is 255. Okay, so let us say student 1 has got 120 marks, student 2 has got 150 marks, student number 3 has got 135, and let us say the last student has got 155, just as an example. Now, I've stored the marks over here somehow, but I have to know that each location over here has to be addressed by a unique identifier. Because let us say when I want to address or when I want to access the marks obtained by the very first student, then I have to know that yes, it is over here. So the memory must be given some number that is corresponding to each of these locations, and that is called as an address. Each location will have an address which is unique. Because if two locations have the same address, well, then the memory would not know where to go. So if memory is organized like this, which it is, we are storing 8-bit numbers, but there are 128 locations. So think of this as a truth table. If there are 128 such locations, how many bits will we need to identify each location uniquely? We will need log of 128 to the base 2, which is 7. We will need 7 bits. So therefore, address will be of 7 bits. So the very first, we can go from 0 to 128 in number. We will call this as decimal address. But in binary, it will be 0, 0, 0, 0, 0, 0, 0. 7 bits. Next location will be 0, 0, 0, 0, 0, 0, 1. Then it will be 0, 0, 0, 0, 0, 1, 0. Like that. And the very last 120, sorry, this will be 127. Not 128, because there are 128 locations. So the address will go from 0 to 127. So this 127 will be 1111111. You can convert this into decimal and see that it is indeed 127. So this is called as the address. Now the data in the memory, that can be anything. So you can convert 120 into binary. You can convert 120 into binary, and you will see that the data that is stored this will be the data that is stored over here. Likewise, or if you make it 8-bit, this will be 0. So like this, if I have 150, it will be this will be 150. So therefore, if I now look into this very closely, at the address 000 0000, it will look something like this. There will be 8 bits of data. So over here we will have 120 initially at the very top location, that is 0 1 1 1 1 0 0 0. At the next location we will have again 8 bits of data, that is corresponding to 150, which is this 1 0 0 1 0 1 1 0. So like this, all of this will be stored. This is called as address. This is called as data. Now let us try to see how these memory bits are represented for different kinds of memories. So, as you may know from a basic computer course, there are essentially two kinds of memory. The first is called as read-write memory. Also called as random access memory or RAM. Means you can put data over there and read also from there as many times as you want. The second type is called as a read-only memory or ROM. That is, you can put data over there just once initially, and then all you can do is read. You cannot rewrite them again and again. Okay. So in this particular course, we will only just see some examples of RAM only, and ROM I leave it to you as a self-study exercise. So there are different kinds of ROM. So what essentially happens is that when we saw this memory structure in the previous page, this is what it looks like. Now you choose any one out of these 8 bits of data. This is called as a single cell. Now suppose I want to do reading and writing over here, both. What can I do? I can do this in a very simple manner using a transistor. I have the address wire, and then I have the data wire. Please note these two are not connected. Now if I have over here an NMOS transistor, N MOSFET, and over here I have a capacitor. So what I need to do is, if I make this address line equal to 1, then this switch will become on. Now whatever is the value of the data, that will be charging the capacitor. So suppose the data is 1, then the capacitor will be charged to a high voltage. And then I can make address as 0, and this capacitor will store that value. This is how you write a 1. Conversely, if you want to write a 0, you again need to make address line as 1 to activate this switch, and then provide a 0 over here. Then if you provide a 0, this capacitor will discharge completely through this path, because this transistor will act kind of now like a closed switch. So this is how you can write 0 or 1. However, if you want to read, what you need to do is, you need to provide a high at the address wire, which will again activate the switch. And then you just need to connect a probe over here at the data line. Don't provide anything, just connect a probe which has a very high impedance. Then whatever is the voltage across the capacitor, that will come across this probe, and therefore you can get this data. So this type of a RAM is called as a dynamic RAM or DRAM. You must have heard about DRAM because it is used a lot in the computer. Now there is one more type of RAM which we will just see, and that is called as a static RAM or SRAM. Now while we saw what is dynamic RAM or DRAM, what happens is that capacitor essentially with time starts discharging very, very slowly. So therefore, if you are accessing that bit after a long time, then you may see that the capacitor voltage might have reduced. So therefore, if the value that was stored was a 1, it may not be stored properly. So this is a drawback of DRAM. The other drawback of DRAM is that it depends on the charging and discharging of the capacitor. Therefore, it is a much slower device. Compared to that, static RAM is much faster. Therefore, it is used in the cache memories of your computer where you need very, very high speed. So, static RAM uses more transistors, but it does not use any kind of capacitors at all. So, therefore, what it does is it essentially makes use of the butterfly structure. So, this is the address wire. So, this is the data wire. Now, what we do is we give the data and its complement both. Data bar. So, here and here, you have two transistors. Which are kind of like those switches, and between these 2 points you have the butterfly structure that is built using NOT gates. So what happens if you want to write the data? Again, you make the address wire as 1. So what this will make is, it will make these two transistors on. And then you just give the data in the data bar. So therefore, this will store ones and zeros or zeros and ones. Then if you make the address wire as 0, this 1 and 0 will be driven continuously by these NOT gates. That's it. So therefore, there is no capacitor in this circuit. So therefore, there will be, the writing process will be very, very fast. And there will be no discharge of the capacitor at all. So this is faster. Next, if you want to read, once again, make the data and the data bar as high impedance monitor probes, and then make the address wire as 1. So whatever is this value, that will come across this resistance, and whatever is this value, this will come across this resistance. This is how you read from a static RAM cell. So in this particular lecture, we talked about the conversion of different kinds of flip-flops, one form into the other. Then we saw how a simple flip-flop can be used as a memory element, and we saw a simple shift register, how you can serially store data into those flip-flops and can also delay them. And then very briefly, we discussed about the organization of memory. In particular, we saw RAM, we saw static RAM, dynamic RAM. We also saw what is the meaning of data and address in memory blocks. Thank you.